Introduction to a power series. Consider the geometric series below using x as the ratio. Okay, so how do I know this is a geometric series to begin with? Consider term to term what's happening. Like, how do I go from 1 to x? Well, I multiply by an x. Well, how do I go from x to x squared? Well, you multiply by another x. So the pattern is you just keep multiplying by an x to go from term to term. This is the pattern that is true of a geometric series. The geometric series that we have already been working with early on, they are series like 3 plus 3 halves plus 3 fourths plus 3 eighths, etc. forever. And you recognize that this is a geometric series, right? To go from term to term, you multiply by a half. This ratio, which is 1/2, is it between -1 and 1? The answer is yes. So that this series is convergent, and it's going to be equal to the value of the first term over 1 minus the ratio. 1 minus a half is a half, and you wind up getting a 6 out of this sum. In general, a geometric series looks like this. You have some sort of first term. The next term is a times some number r, and the next term is a times r squared. Right? You're just multiplying right by an r to go from term to term, plus ar cubed, etc. And we learned that if the ratio is between -1 and 1, then this will be equal to the first term, which is a in this case, divided by 1 minus the ratio. Now, if a was 1, you would have this formula. Well, now I'm just rewriting the exact same thing that we have here, but using x instead of r for the ratio. You have this statement, which is only true if the ratio is between -1 and 1. And then let's just examine it here in summation form. If you started with this summation over here and you plugged in n equals 0, you get x to the 0. That gives you this 1. Then you plug in n equals 1 next, right? And then you'll get x. And then plug in n equals 2, you'll get x squared, etc. And then you go forever. So the dots, right? You never stop. The thing that makes this series different than the series that we've been considering so far is that this series has a variable in it. All the other series that we tested, whether that series was convergent or divergent, involved just series of numbers, adding up numbers. So now we're starting to explore, well, what happens if I have a variable as a component in my series, and then I start to ask myself, hey, for which values of this variable is the series going to be convergent? When you have a series involving increasing powers of some function of x, it's going to be rare that we can say what that series is equal to. Of this whole statement here, this part right here, like what the series is equal to, is often going to be missing. We're only going to be able to talk about whether the series is convergent and for which values of x. This right here is called the interval of convergence. It's all the values of x for which the series is convergent. And also there's another term called the radius of convergence. All intervals have an x-coordinate that is the center of that interval. The radius is how far from the center to either end of the interval you go, right? So if you look at, here's 0, here's -1, here's 1. And if you say this is the interval of convergence, then the center, of course, is 0. And then you go 1 and 1 in each direction. And it's that 1 that's called the radius of the interval. So pretty much the radius of an interval is half of its length. So this length from -1 to 1 is 2. Half of that length is 1. And so we say that the radius of convergence is 1 in this case. This particular interval of convergence for the geometric series was determined using analytical methods, but I'm going to show you a second way to determine what the interval is. And that's going to require us to walk back to the ratio test. When you took a series and you did the n plus first term and divided by the nth term and put it in absolute value and did a limit as n goes to infinity, and you get this number k. If k was less than 1, then the series was absolutely convergent. If k was more than 1, then the series was divergent. And if k was 1, the ratio test was inconclusive. Apply the ratio test to the power series and see if we can use that test to determine the values of x for which k will be less than 1. In other words, for which the series will be absolutely convergent. And I'm going to apply the ratio test to this series. So we rewrite the summand, but all the n's change to n plus 1's. And then you divide that by the summand. Then you put this in absolute value, and then you simplify the expression as much as you can, and then you ask yourself what this approaches as n goes to infinity. You leave x fixed. Imagine x as some unknown or unspecified constant, and then you let n approach infinity and see if there's a limit. Now in this particular case, x to the n plus 1 divided by x to the n simplifies to just x. Right? All the n's happen to disappear in this case. So as n goes to infinity, what happens to this expression? Well, this expression turns into a constant as far as n is concerned. So this approaches as n goes to infinity. This expression would stay the same because there are no n's. This is the k. Now the series will be absolutely convergent if this value k is less than 1. So that means absolute value of x has to be less than 1. And then the way to turn an absolute value less than a positive number into an inequality that doesn't involve absolute value is to create a double inequality where x has to be between the negative and the positive of that 1. All right, so this leads to that the geometric series, according to the ratio test, is convergent if x is between negative 1 and 1. And remember that our test was inconclusive if k is 1. K in this case was absolute value of x. If you solve this, this gives you x is equal to 1 or negative 1. The ratio test itself is not conclusive if x is 1 or negative 1. And the question now on the table is whether or not the 1 and negative 1 should be included in our interval of convergence. Now, ahead of time, we know that they should not. But right now we're sort of taking the stance that we don't know that, and we're trying to use this ratio test to confirm. Let's explore these two cases, 1 and negative 1, separately. If x is 1, you go back and you rewrite the series and you just change the x to a 1 and you see what the series looks like. Let x be 1. And then our series looks like this. So 1 to the n will be equal to 1 for all n. So this is just a series of 1s, which really means you're just adding 1 forever. You add 1 forever, you get something infinite. This is a divergent situation. And then you test the other endpoint and see what the series looks like if you're using negative 1 instead. This is a funny series. It's 1 minus 1 plus 1 minus 1 plus 1, etc. forever. Now, as a sequence, negative 1 to the n does not have a limit. It does not approach 0. Therefore, as a series, by the divergence test, this diverges. All right, so these are the mechanics that confirm what we already knew, that the interval of convergence for a geometric series is, in fact, negative 1 to 1, and it does not include either endpoint. And the radius is 1. As far as the radius is concerned, if the interval had included the endpoints, we would still say that the radius is 1. The general form of a power series is below. The geometric series was just a very simple example of a power series, just to lead us into this idea. And the more general form of a power series is that you have increasing powers on some function. It doesn't have to just be x, it could be something else inside there. And then we also have the potential complexity of coefficients that are changing from term to term. Now, in the case up here, the coefficients were all 1. But in general, this is what a power series looks like. Now, what we're going to do for the next 3 or 4 examples is effectively repeat what we did here. We're going to do the ratio test, get some k, set k less than 1, and solve for x to find the interval of convergence. And then we're going to test the endpoints using other tests other than the ratio test to determine if the series will converge at the endpoints of the interval of convergence. Find the interval and radius of convergence of the power series. All right, so we're going to begin by setting up the ratio test. We do absolute value. I rewrite this, but I change all n's to n plus 1's. Right, and then I divide all this by, and then I just write down the summand, unchanged. I'm going to do a little bit of manipulation here as well. I'm going to choose to put this power on the x and on the 4 separately, and then multiply instead, and then I'm going to reciprocate this and also move this power n to the 4 and the x separately. I'm going to regroup and write this as a bunch of fractions by putting things over their similar counterparts. Then, if you recall, there's a property about doing absolute value of a product. If I have a times b and it's inside absolute values, then you could just absolute value the factors separately. Now be careful you don't do this for a sum. For example, what if a was negative 1 and b was positive 1? Right? If you add these together first, you get 0, and absolute value that next, you still get 0. But if you absolute value them separately and then add, you get 2, right? So you don't get the same thing. We have 4 to the n plus 1 divided by 4 to the n, right? Just recall that 4 to the n plus 1 could be written this way. 4 to the n's will cancel, and you get just 4 to the 1. So the first fraction just becomes a 4. The second one becomes x for the same reasoning. And the other one we can't simplify. It just stays n over n plus 1. Now I'm going to use the idea that the absolute value can narrow in on each of these factors. So you could do the absolute value of 4 by itself, absolute value of x by itself, and absolute value of this n over n plus 1 by itself. And of course, some of these absolute values aren't needed. I mean, the absolute value of 4 is just 4. The x, though, we need to keep the absolute values on the x because x is an unknown. So that's going to stay in an absolute value, and that's important. The third expression right here, the n's we're assuming are essentially positive. Like n is going to positive infinity. So n over n plus 1 is positive. So the absolute values aren't needed. Now you have to do a limit as n goes to infinity. Well, 4 is constant with respect to n, so is x with respect to n. We're not letting those change, but we're just asking ourselves what happens to this part when n goes to infinity. And that's a balanced rational function. You just divide the leading coefficients or use L'Hopital's rule, and that will approach a 1. And of course, this expression is just 4 times absolute value of x, and this is the k. Now, if we want convergence of the series, we want our k to be less than 1. The series will be absolutely convergent if k, which is the same thing as 4 times the absolute value of x, is less than 1. So we got to solve this statement right here for x. The first thing I want to do is divide both sides by 4, and then write this as a double inequality. And there's our interval of convergence, at least the open interval. Let's test what happens to the series when x is negative 1/4. Now, the ratio test is not useful when x is the endpoints, because if k is 1, in other words, if 4 times absolute x is 1, in other words, if absolute value of x is 1/4, in other words, if x itself is 1/4 or negative 1/4, that the test is inconclusive. So I can't use the ratio test to test the endpoints. To test the endpoints, I'm going to just plug the endpoints into the series and make it a series of numbers, and then use a different test. Let's do the right endpoint first. So rewrite this series with that choice of x. We get 4 times 1/4 inside those parentheses. 4 times 1/4 is 1. And also, I don't need to write the starting and ending values. We know this is a series. It goes to infinity. It doesn't really matter where it starts, because all that matters is whether the tail is convergent or not. Anyway, this becomes a series of just 1 to the n over n, but that's just the series of just 1 over n. And the series of 1 over n is divergent because this is the harmonic series specifically. This adds to infinity. I should always still cite what test you're referring to. So let's see what happens when x is negative 1/4. Rewrite the series. Well, this is 4 times negative 1/4 is negative 1. This is a negative 1 inside the parentheses, not a positive 1. This produces an alternating series, and therefore you focus on the non-alternating part. This does decrease to 0. So this converges by the alternating series test. Okay, so our final answer then, our interval of convergence. This is the basic structure of it, but now we're going to say that it's also convergent at the left endpoint, right? We did get convergence when I tested negative 1/4, but I got divergence, right, when I tested positive 1/4. So I want to exclude positive 1/4, but I want to include negative 1/4. That's my final interval of convergence, and the radius of convergence is 1/4 in this case. All right, I'll go a little bit more quickly this time. I'm going to rewrite the series, but change the n's to n plus 1s, and then multiply by the reciprocal of that summand, as it is written. 4 minus x to the n plus 1 over 4 minus x to the n just becomes 4 minus x. When I group the n squared over the n plus 1 squared, I could do this. I could just say this is the same thing as n over n plus 1, and that's being squared. And then we still have absolute values. Now these absolute values, I'm going to narrow in on this and this both, but the expression on the right, this is always positive, so the absolute values don't need to stay on that, but they do definitely need to stay on this. And don't do an absolute value of the pieces separately, because this is not a product right here, this is subtraction. Now we do a limit as n goes to infinity, so I'm using arrow sign. Imagine the x is fixed, but the n's are going to infinity, and here we have an n over n plus 1. That's going to approach 1, and then 1 squared is still just 1. So this really just approaches this expression. This is our k, and I set it less than 1. This creates an inequality I want to solve for x. You have something in absolute values less than a constant. You can instantly turn this into a double inequality, and then we can isolate the x that's in the middle in the classic way. Just whatever you do to the middle, you do to the left and right sides as well. So let's begin by subtracting 4 from each component of this double inequality. Then multiply everything by a negative 1. You need to remember that when you take an inequality and you multiply or divide both sides, or in this case all 3 parts, by a negative number, you need to change the directions of those inequalities. I get positive 5 is greater than x, which is greater than 3. This should be an inequality that makes sense. Right? This is saying that x is more than 3 but still less than 5, so x is between 3 and 5. This is an inequality that doesn't make any sense. Of course, you could now write this and reverse it and say this is saying the same thing as that x has to be more than 3 but less than 5, right? If x is between 3 and 5, then the series will be convergent according to the ratio test. But the ratio test is inconclusive at the endpoints of this interval. So I need to test the 3 and the 5 separately. Here we go. Let's test what happens when x is 3. So I'm going to rewrite this series, but change the x to a 3. And I don't need to bother saying where the series starts. right? This becomes the series of just 1 to the n, but 1 to the n is just 1, so it's really just a series of just 1 over n squared. And this is a convergent p-series. Okay, let's test the other endpoint. Let's test 5 next. So rewrite the series, but change the x to a 5. This becomes an alternating series because that's a negative 1 inside there raised to the n over n squared. And if you just look at the sequence, 1 over n squared does decrease to 0. And if the sequence decreases to 0 and then you make it alternate and then you add them up, then you're always going to get a convergent series by the alternating series test. All right, so this particular series converges at either endpoint. So my interval gets to include both. This interval is centered at 4, and you go 1 in either direction. So the radius of this interval is 1. And there's our answer for this one. This next one, okay, let's set this up. We have the absolute value of, I'm going to put n plus 1s, and then multiply in the reciprocal of that summand. I'm going to simplify the x's over each other. That's just going to become a simple x. And then the factorials, if you recall, if you have an n factorial over an n plus 1 factorial, both of these really just mean n times n minus 1 times etc. down to 2. And the bottom one is the same thing, but starts one number higher. So the n's and below are going to cancel, leaving just the n plus 1 in the bottom. All right, so when I simplify the factorials, I get 1 over n plus 1. Now the absolute values are on the whole thing, but when you narrow it down to this one and this one separately, only on the x matters, because this part right here is positive. So you don't need to keep the absolute values on that. Okay, so now we say, okay, imagine that x is fixed, and we're going to let n approach infinity. Well, this will shrink to 0, no matter what x is. Now imagine that x is fixed. So even if x is a trillion, doesn't matter how big x is, when n goes to infinity, this power of n will dominate this constant. So this approaches 0 no matter what x was. This is actually a special case. And this 0 is still our k, and 0 is less than 1. So we always get absolutely convergent, meaning that the series converges for all choices of x. So our answer to this one here will be the interval of convergence is negative infinity to infinity, and the radius of convergence is infinity. Notice I flip-flopped it. I put the factorial above the exponential. So right away, I can conclude something like this. No matter what x is, just imagine x is fixed and let n go to infinity. Because factorials dominate exponentials, that this is going to go to infinity. As a sequence, when you do the series, when you add them up, you're going to get a clear case of infinity. The basic divergence test says that if a sequence does not approach 0, then the series has to be divergent. Well, let's just do the ratio test to confirm that. So we have a 2 times n plus 1 factorial divided by an x to the n plus 1 and absolute value, and we're going to multiply that by the reciprocal of the original summand. The 2's are going to cancel. The n plus 1 factorial over n factorial is going to become an n plus 1, and then the x's over the x's, that's going to leave just an x down in the denominator. And all of this is an absolute value, and when you do absolute value of a fraction, you could do absolute value of the numerator and denominator separately. So I only really need the absolute values on this x. Now we ask ourselves what happens as n goes to infinity, and x is some fixed constant. Well, as n goes to infinity, this approaches infinity over a constant, and infinity over a constant is infinity. So this approaches infinity, this is our k, and this k is more than 1. So this is saying that the series is divergent no matter what x is. We have to be careful here. When I have this expression here, we're assuming that x is not 0, because otherwise this expression wouldn't make sense. So x can't be 0. If it's any other value, the series will be divergent. So this diverges for all choices of x. We'll consider this problem done. Let me squeeze in a really quick impromptu question here. And let's do this just one more time to show something that can happen. Let's do a series of, let's put an n factorial times x to the n. Okay, let's set up the ratio test. So we have a absolute value of n plus 1 factorial times x to the n plus 1. There's no fraction here, so I'm just going to go ahead and divide it now by the original expression, n factorial x to the n. All right, the factorials will simplify to just an n plus 1 up top, and the x's will simplify to just an x up top, and the absolute value will narrow down to just the x. X can be 0 in this case. It's different from this case over here where it was in a denominator. So x could be 0. Let's assume it's not 0 though for now. So this will approach infinity if x is not 0. This is our k, and k is more than 1. So the series diverges, but if x is not 0, we get a divergent series. But what happens if x is 0? Let's go ahead and actually get a starting value. But if n is 1, and plug in a 1 here for all the n's, we get just a clean x to start, and then the next term will be a 2x squared, then a 3 factorial, which is 6x cubed, etc. what we've just established is that if x is not 0, this will be a divergent series. But what if x is 0, right? If you plug in 0 for all the x's here, you get a series of zeros, which is 0. So it's trivially convergent. Okay, so then this series, n factorial times x to the n, converges if and only if, so IFF, x is 0. So in this case here, we say that the interval of convergence isn't really an interval at all. It's just 0 itself. And then we say that the radius in this case is 0.